Hey, this is the alveolar gas equation. It's a really important equation in respiratory physiology, and it helps us understand the partial driving pressure of oxygen within the alveolus down to the blood. It also helps us understand different pathologies and how we can fix them in medicine, which I'll go into more detail in later videos. It starts off with PaO2, and remember in respiratory physiology, capital A is always for the alveolus and P representing partial pressure. Partial pressure we normally measure in millimeters of mercury. Now, to begin with, this first part of the equation is to do with how much oxygen gets into the alveolus, and because there's also CO2 being exchanged, this part of the equation represents CO2 within the alveolus. Remember, within the alveolus, there's only a certain amount of space, and CO2 takes up a part of this space and removes some of the pressure, which limits how much oxygen can get down into the alveolus as well. To begin with, we need to know our inspired FiO2. So it's FiO2 times, and we need to know what our partial pressure is down in the alveolus as well. Now, atmosphere at sea level is 760 millimeters of mercury, but as we breathe air in, it becomes 100% humidified, which I talk about in my absolute first relative humidity video. But just remember, at 37 degrees, the partial pressure of vapor pressure is 47 millimeters of mercury, and this occurs at about 4 to 5 centimeters above the carina in the trachea with inspired air. So this is the partial pressure of water. So it's atmosphere minus water times your FiO2, and this gives us the amount of oxygen that gets down to the alveolus. But that's not the equation completely, as we need to take into account how much CO2 is also sitting down in the alveolus as well. PaCO2 is used, as this is the partial pressure of CO2 within the arterial blood. But remember, this is in the arterial blood, not in the alveolus, so we need to account for the exchange ratio of how much CO2 exchanges from the artery into the alveolus. In textbooks, you'll come across something called respiratory exchange ratio, which is in orange here, or respiratory quotient. I talk about this more in my video about this topic, but essentially they're equal at steady state, so I'm using respiratory exchange ratio here. In the Western diet, this is 0.6, and in a normal person sitting at rest, the PaCO2 would be about 40. So let's break this equation down with some actual numbers. So FiO2 is around 21%, which is 0.21. At sea level, atmospheric pressure is about 760 millimeters of mercury, and vapor pressure, as we mentioned, with 100% humidity at about body temperature 37 degrees is 47 millimeters of mercury. And we already mentioned that PaCO2 is about 40 with a respiratory exchange ratio of about 0.8 on a Western diet. So working for our equation, we begin with these brackets here. So 760 minus 47, so atmosphere minus vapor pressure is 713 millimeters of mercury. Of this, 21% is the partial pressure of oxygen, so times 0.21, which becomes 149.73 millimeters of mercury. Going back to the CO2 part of our equation, 40 millimeters of mercury divided by 0.8 is 50 millimeters of mercury. So our equation becomes 149.73 millimeters of mercury minus 50 millimeters of mercury. Remember, this is the oxygen part of the equation, this is the CO2 part of the equation. Then when we get down to the alveolus, essentially it's 150 minus 50, so our PaO2 is about 100 millimeters of mercury. So now we've discussed the alveolar gas equation in depth. I'm going to talk through each of these steps so that we can understand how in the real world the PaO2 can be affected by these different variables. PaO2, just to remind you, with a capital A, is the partial pressure of oxygen at the level of the alveolus in the lungs. Our first variable is inspired oxygen, so our FiO2. Now this variable we can change by giving the patient oxygen. We can get this all the way up to 100% if someone was intubated, ventilated, or had an NIV mask on with a perfect seal. You can see that if this is increasing, then this variable will increase as well, meaning that our total PaO2 will increase by the end of the equation. The next variable is our partial pressure of the atmosphere. So generally we can't really control this, but I'll take you to two extremes. So at sea level it's 760 millimeters of mercury, but then at one extreme, if we were at the top of Mount Everest, this would be about 336 millimeters of mercury. So you can see that it's almost halved. Because this halves, it means that if we kept our FiO2 at 21%, our PaO2 would decrease. This explains why mountain climbers carry oxygen with them, because they need to make up this part of the equation to compensate for the decrease in partial pressure of atmosphere to remain oxygenated and keep our PaO2 elevated. The other extreme is in hyperbaric medicine, where you can put someone in a pressurized container and you can increase this variable. So to put this into an example, if you doubled 760 millimeters of mercury, this would become 1,520 millimeters of mercury. You'd minus your vapor pressure, which at body temperature is largely constant, so it'd be 47 millimeters of mercury, which becomes 1,473 millimeters of mercury. If you kept the inspired oxygen at the same level and you multiplied it by 21%, so 0.21, this would equal 309 millimeters of mercury. So our PaO2 in this oxygen part of the equation would equal 309 millimeters of mercury. You'd then minus off your CO2, which would then give you a higher PaO2 in total. The vapor pressure we can't really change because it's warm to body temperature. And at body temperature at about 37 degrees, when we get to about 4 to 5 centimeters above the carina in the trachea in the lungs, is about 47 millimeters of mercury. This is largely unchangeable and was kept constant. Then there's this part of the equation, which is the partial pressure of CO2. PaCO2 is a byproduct of cellular metabolism, and we can't change this very much. And when buffering systems are oversaturated, our PaCO2 will increase, meaning that more CO2 will need to diffuse from blood into lungs. The respiratory exchange ratio is constant as long as CO2 and oxygen are constant, and respiratory quotient, which is sometimes substituted here, we've talked about in a previous video and explained further, but it's largely dependent on diet and what fuel source is being used. We can technically change this, but in states of critical illness and for practical reasons, we can't really adapt this part of the equation.